My name is Lily McIntosh, and today I'll be presenting modeling the interactions between blue whales, minke whales, and krill in the Antarctic region. This presentation will include a species introduction, the motivation and history behind the model, an overview of the Hollings Type 1 and Type 2 functional responses. I'll introduce the model and then I'll go over the nonlinearity and the resemblance to the Hollings Type 2 functional response. I'll conclude by showing the results of the model. This is a multi-species model. I would like to introduce you to the 3 species covered in this presentation. Today, we will analyze 2 different types of baleen whales in the Antarctic region. Baleen is essentially a form of teeth that act as a filter feeding system inside the mouths of baleen whales. Most baleen whales, particularly the 2 we'll be studying today, feed primarily on krill. During the years 1904 through 1977, baleen whales were substantially harvested. The first species I would like to introduce is the blue whale. This is a large baleen species that was harvested legally between 1904 and 1964. They were so heavily exploited that their population was almost extinct in 1970. Because blue whales are so large, they eat about 3 tons of krill per day. I'd like you to imagine how this would affect the krill population. Next, we have the minke whale. This is also a baleen species that was harvested between 1970 to 1986. This is directly after the blue whale exploitation. However, it was harvested less dramatically as the blue whale. Because this is a smaller species, they eat far less krill than blue whales. Lastly in our model is the food source to most baleen whales, which is krill. It's definitely the food source of our 2 species of interest. I would like to give a motivation for this model. In this Antarctic region, the ecology tends to follow a bottom-up food chain. For example, if we were to assume that there were limitless krill and no harvesting of baleen whales, the blue whale and minke whale should be able to grow and reproduce their population exponentially. However, this is untrue because as both populations increase, they would eventually exceed the population carrying capacity of the Antarctic, and there would be fluctuations in the population sizes. Because of the harvesting of blue whales, we get a similar situation to the limitless krill mentioned previously. Because blue whales feed on such large amounts of krill, when they were harvested to almost extinction, this left a large amount of krill surplus for species like the minke whale to feed on. This krill surplus has impacted the minke whale population by reducing the birth rate at times due to surpassing the assumed carrying capacity of minked whales. This leads us to investigate just how the population was impacted, and this is what motivates the model. Before introducing the model, I would like to give a background on the Hollings Type 1 and Type 2 functional responses. These functional responses are able to model different types of predator and prey populations. However, this is different to a predator and prey model that we're used to seeing. The Hollings functional responses are functions of the prey population's density and the prey consumed by the predator. For the Holling Type 1, it is assumed that there's a linear increase in prey consumed with the density of the prey population. For most cases, this prey consumption is only up to a maximum, and then the prey density and prey consumption are constant rates. If you look to the graph on the left, I've illustrated a Hollings Type 1 in maple. The parameters of the function y equals alpha times t times x are as follows. Alpha is what Hollings called a discovery rate. It is a constant of proportionality that describes how likely the predator will come in contact to the prey. T can be described as an average time spent searching for the prey, and x is the prey density where the function is linearly dependent upon it. For the Hollings Type 2 functional response, we can now assume that processing and searching for prey are mutually exclusive behaviors. Because of this, we can take the value of T sub s used in the original Hollings Type 1 equation and change it to reflect this assumption. T sub s will now be described as T sub t minus by. This means that the time spent searching for prey is now reduced by a time allotted to process the prey. The time allotted to process the prey is represented by the by term. After making this substitution, the Hollings Type 2 function can be described as this equation. This is nonlinear, as the prey consumed initially rises as the density of the prey increases, but then it levels off as the density of the prey continues to grow. I've illustrated this Hollings Type 2 functional response with a graph in Maple that's shown on the left. Now that we have been over the basis of this model, we can start to look at how it was developed. The two main assumptions made are that this model assumes a Hollings Type 2 functional response and that the consumption and birth rate of the predators are dependent only upon the density of the prey and not the density of the predators. It is also assumed that other krill-eating species do not affect this population for simplicity of the model. The first equation in this multi-species system models the biomass of krill. I will mention that this is the most extensive equation due to the fact it is the prey of two predators. I will briefly go over the parameters in this equation. B sub y is the biomass of krill in the start of year y. R is the intrinsic growth rate of krill. K is the carrying capacity of krill in the unit tons. Lambda b is the maximum per capita rate of krill consumption by blue whales in the units tons per year. N sub yb is the number of blue whales at the start of year y. B sub b is the level of krill biomass at which the per capita blue whale consumption rate drops by 50%. Lambda m is the maximum per capita rate of krill consumption of minke whales, also in the units tons per year. N sub ym is the number of minke whales at the start of year y. B sub m is the level of krill biomass at which the per capita minke whale consumption drops by 50%. Now, if you would draw your attention to the last term on the right side, we can see that this is the rate at which krill is consumed by the population of minke whales. This term is subtracted from the krill biomass, which makes sense because the krill are being consumed. This term is dependent upon the density of the krill biomass, which reflects the Hollings Type 2 functional response. The term just to the left of that represents the krill consumption by blue whales. Once again, this function is dependent upon the density of the krill, also reflecting the Hollings Type 2. This term here is the krill's natural increase. It is dependent upon the growth rate of the krill biomass and the krill carrying capacity of the krill in tons. I will now go over the equation that models the population of blue whales. We can already see that it has less parameters due to their main threat to life is natural mortality and being harvested. First, let me briefly introduce the new parameters that we did not see on the previous slide. Mu b is the maximum per capita birth rate for blue whales. Mb is the annual rate of natural mortality of blue whales. And C sub yb is the catch in year y of blue whales from the Antarctic region. The last term on the right side of the equation represents the amount of blue whales harvested in that year. This is why it's being subtracted in the equation. Because of the harvesting, the population is reduced. If you remember how I mentioned that they were heavily harvested until the 1970s, I would like you to think about how this would affect their population. This term here reflects the natural mortality, also reducing the population. And here we have the natural increase of blue whales. Once again, this term reflects the Halling type 2. It's dependent upon the krill density. The model for the minke whale population is extremely similar to that of the blue whales. Here we have the reduction of the whale population due to harvesting, the natural mortality of minke whales, and the natural increase of minke whales, which is dependent upon the density of their prey, krill. I will briefly remind you of the places we find nonlinearity within this model. For krill, we have these three terms that are all dependent upon the prey's density. This relationship causes the equation to be nonlinear, and it reflects similarities to the Halling's type 2 functional response. For blue whales, their natural increase in population is dependent upon the krill's density. We also have this same nonlinear relationship for minke whales. This model was simulated between the peak harvesting years of baleen whales, the years 1900 to 1990. The parameters for this simulation were estimated by using equilibrium analysis to find the original population of all three species in the year 1900, and by research. We see quite a couple different trends here in the results of this model. As the blue whales are harvested, the krill surplus increases rapidly, just as we would suspect. With this increase, we see that the minke whale population also increases. This is due to the krill surplus and being able to consume more food. Directly after the large increase in minke whale population, the krill biomass plummets. This goes back to what I mentioned at the beginning of the presentation, a bottom-up food chain. The minke whales had increased their population so much that they outgrew their food resource, and the rate at which the minke whale population consumed krill was greater than that of the krill's natural increase. By the beginning of the 1970s, minke whales were beginning to be harvested, which causes the population of krill to rise again. To quickly summarize this presentation, the baleen whale population was greatly affected by harvesting in the early 1900s. We are able to model these effects by applying the Halling functional responses. I would like to thank you for your time. The model and experiment used in this presentation is based on Morey and Butterworth's journal article, Consideration of Multi-Species Interaction in the Antarctic, a preliminary model of the minke whale-blue whale krill interaction.